Hello friends, welcome to lecture number 6 of complex analysis. Today our topics of discussing are function of complex variable, Cauchy Riemann conditions, these are the conditions, and solutions of exercise problems of mathematical physics books by H.K. Das. Okay, so now you already discussed about those topics here. You see complex numbers, graphical representation, Euler's formula, De Moivre's theorem, roots of complex numbers in last 5 video lectures. Okay, links are given in the description box. Today we're going to discuss about functions of complex variables, analyticity and Cauchy Riemann conditions. Okay, and also I'm going to show you how to solve problems based on this topic. And let me tell you one more thing. I have provided the link of the playlist of Laplace transformation. If you need lectures on Laplace transformation, you may watch those videos. Okay, so now before we start, please subscribe the channel if you are new to my channel. Also share with your friends and help me to grow my channel, inspire me to create new videos for you, and stay connected. And also hit the bell icon so that you get notified when new video will be uploaded. Now let us discuss about function of complex variable. Here you can see function of complex variable. Okay, so if we consider here you can see if z is a complex number, then here of the form, suppose x plus iy. So then here you see where x is the real part and y is the imaginary part, right? Then the function f of z here, then the function f of z is said to be a function of complex variable. Okay, it's said to be a function of complex variable denoted by w is equal to f of z, okay, u plus I v. That means here u and v are the functions of x and y. Okay, u is the real part, v is the imaginary part of the function. Okay, if f is a function of complex variable, then f of that complex variable it also a complex number, right? So u plus iv, it is in complex form, so here u is the real part and v is the imaginary part, right? Then they are functions of x and y. Also u and v are the functions of x and y. So they are functions of x and y. It doesn't mean that x is function of u is function of x only. It may be function of both x and y, and similarly v also, it may be function of x and y both. Okay, so now u is a function of x and y, v is also a function of x and y, we can say that way, right? Now you see, if f of z is single valued function means that for one value of z, or you can say for its value of z in its domain, it must have unique corresponding value in its range. Okay, for one z you're gonna have one, you never gonna get it repeated. Okay, for different z's you cannot have the same result. Okay, that is single valued functions. Okay, now you see f of z tends to w naught, suppose, as z tends to z naught, suppose, then we can say that limit of f of z when z tends to z tends to z naught, then limit of f of z is w naught, we can say that way, right? Now derivative of f of z you can write this way, right? Now you see, let w is equal to f of z, dw be the increment, delta w be the increment in w, that means fz, when delta z is increment in z. Okay, that means when z is changed by del z, then w, which is equal to f of z, changed by delta w, right? That is the meaning. So hope you have understood. In that case, we can write this way: w plus delta w is equal to f of z plus delta z, because when we have w is equal to f of z, then due to change in z, there will be change in w, and that's how we have got this relation, right? So hope you have understood this. So then what we can say, it implies delta w is equal to f of z plus delta z minus w, and we know that w is equal to f of z, so we can replace this w by f of z. So, and doing so, we have got this result, f of z plus delta z minus, this is suppose equation number 1. I have taken this as equation number 1. Using 1, we have got here f of z instead of w. Okay, using 1. So hope you have understood this. Now let us divide both sides by delta z. Then we have got this, dividing both sides by delta z, then taking limits. So this should be increment here. This spelling is wrong. Okay, now it is correct. Now let me go to the next slide. Okay, let me continue this. Let me take a new slide. This is the last step we have got, right? Now let us take limit on both sides such that delta z tends to 0. Then this is nothing but derivative of w with respect to z, or you can say derivative of f of z. And similarly on the right hand side, let us keep as it is. Okay, so here the left hand side, this is the nothing but f dash of z, that means derivative of f of z, which is equal to this, right? So we have got this. And remember one thing, z may approach to 0 along any path. That means it independent of path. Okay, so now you see, a single valued function f of z is differentiable. That means differentiable at this point, z is equal to z naught, when the limit exists at this point, or you can say this is equal to limit z tends to 0 of this exist, right? For this point z is equal to z naught, we're gonna write here z naught. Okay, z naught, we're gonna write here z naught. Just wait, f of z naught. If this limit exists, we can say then this function differentiable at this point, right? So then you see, this function f of z is said to be analytic. Okay, if this is differentiable at this point, then this is also analytic at this point, z is equal to z naught, right? Z is equal to z. So hope you have understood this. And the point where it is not differentiable, that is called singular point. And the point where this function is not differentiable, that is called singular point. So let me write here. That is called singular point, right? So now let me go to the next slide. So now you see necessary conditions for a function f of z to be analytic. These conditions are called Cauchy Riemann conditions, right? So these are Cauchy Riemann conditions. So if a function f of z of this form v plus iv to be analytic, it must satisfy the following conditions. So let me write the conditions here. In the region R. So this function to be analytic at all the points in this region R, it must satisfy following conditions, and those conditions are, let me write the conditions below. Del u by del x, that must be equal to del v by del y, and del u by del y must be equal to minus del v by del x. Okay, so this condition, the second condition, can be written this way also, del v by del x minus del u by del y. So these are CR conditions, or Cauchy Riemann conditions, you can say. Okay, Cauchy Riemann conditions. Okay, these are Cauchy Riemann conditions, or you can say CR conditions. So here, provided that this derivative del u by del x, del v by del x, del u by del y, del v by del y, these conditions are exist. Okay, this derivative exists. Okay, so now you see, now let me go to the next slide and let me prove this conditions. Okay, so here you see, so let us consider this be an analytic function, f of z be an analytic function at a region R where u and v are the functions of x and y. Okay, and suppose here one more thing, z is equal to x is equal x plus iy, and suppose delta u and delta b, these are the increments in u and v corresponding to the increments in corresponding to the increments delta x and delta y in x and y, right, respectively. Okay, then we can say that f dash z is equal to limit z tends to 0 f dash z plus delta z minus f of z divided by delta z. So what we can do here, so limit delta z tends to 0, so f of z plus delta z, here you see. So as we have considered that these two are increments in u and v, so as we have function f of z is this, then when you have f of z plus delta z, then there must be also increment in u and v, which can be written this way, that is u plus delta u plus I into v plus delta v, right? So hope you know these things, hope you have understood this. So now let me proceed. So then we can write that way, right? Then minus f of z is u plus iv, right? Let me write within bracket by delta z, right? So let me write this way. So here you can see, if you simplify this, if you open the brackets and cancels the negative and positive terms, so here you can see this is delta z, and this is negative iv, and this is positive iv, cancels, negative u, positive u cancels, so we are left with this term only, right? So now we have got this. Now let me copy this and let me go to the next slide. Okay, so here you see, so this is the last step we have got, right? Now it can be written in this way, separately delta u by delta z plus I limit delta z tends to 0 delta v by delta z, right? So now you see, let me take this one as equation number 1. Now case 1, as delta z tends to 0 is independent of path, so let me take any path that let me take the path of real axis, that means along x-axis. So delta z approaches to 0 along x-axis, that means real axis, and on x-axis the equation of x-axis is nothing but y is equal to 0, right? Hope you know these things. So then z will be equal to, z is nothing but x plus I y. So here as y is 0, as the y is 0, right? So that's why putting y equal to 0 we're gonna get z is equal to x, right? So if z is equal to x, then we can write delta z is equal to delta x, and delta y is nothing but 0 as y equal to 0. So using these results in equation number 1, so from equation number 1 we're gonna have this result. So delta z gonna be replaced by delta x, as we have got delta z is equal to delta x. So you're going to replace it by delta x. This delta z is replaced by delta x. So hope you have understood this. So then we're going to get this result. This is suppose equation number 2. So here you see, this can be written this way, right? Partial derivative of u with respect to x, then plus I derivative of v with respect to x. This is equation number 2, suppose. Now again, if we approach to z, if delta z approaches to, if delta z approaches to 0 along the imaginary axis, that means along y-axis, of which equation is x equal to 0. Equation of y-axis is x equal to 0. Then z becomes equal to x plus iy. X is 0 now, so it's going to be iy. So delta z going to be I delta y, right? And delta x going to be equal to 0. And using this result in equation number 1, in this above equation, in equation number 1, we're going to have this result, right? We're going to have this. So here we're going to replace the delta z by I delta y, right? So, and doing so, we're going to have this result, okay? Delta u by I delta y plus again I limit delta y tends to 0 delta v by I delta y, right? So we're gonna get this, okay? It can be written in this way, right? So we have got this. So now what we can do here, you can see I cancel, and we can in the first term we can multiply I and I with the both numerator and denominator are multiplied by I. Then it's gonna be I minus 1, I into I minus 1, and here is I, so it's gonna be minus del u by del y, and there will be a I, okay, minus I del u by del y, and plus del v by del y. This is equation number 3. Now you see, in 1 and 3 both are f dash of z, right? And if this function is differentiable, then we can equate equation number 2 and 3. So here, if you compare the real and imaginary parts on the right hand side, so equating 2 and 3, what we're gonna have? We're gonna have, this is the real part here, and the real part here is this, okay? Del u by del x will be equal to, you know, del v by del y. This is the first condition of Cauchy Riemann condition, okay? And the next one, if you compare the imaginary part, this one, del v by del x with this, okay, both consist I, so both are imaginary part, then you're gonna have this result, okay? So these are the Cauchy Riemann conditions, right? Cauchy Riemann conditions. So hence it is proved, okay? So you can, if you want to write this condition, this second condition in this way, you can write del u by del y. You can write this one first, then minus del v by del x. You can write this way also. This is v, okay? and this one is u. So this is Cauchy Riemann condition. So now let us take a question. So we need to show this function, this complex function is analytic function. This is the analytic function at all the points x is equal to y. Okay, so now let me write the solution, and here the given function of complex variable is this. Okay, so now here u is equal to the real part is x square and v the imaginary part is y square. Okay, now let us differentiate partially u with respect to x, then we're going to get twice x, and let us differentiate v with respect to y, then we're going to get twice y. And similarly, if we differentiate with respect to y, if we differentiate u with respect to y, as it is a function of x, so that's going to be 0. And similarly, del v by del x also, it's going to be 0 because v is function of y only. So here you can see in the question it is given that for first let me write the CR conditions. These are the CR conditions or Cauchy Riemann conditions. So we're going to use here. So we're going to check this function. We're going to check that this function does satisfy this condition or not. So here you can see this imply minus in order to check this, let me write this way, minus del v by del x. So if you as this is 0, you can put positive or negative, it's going to be same, nothing going to be changed here. So now you see here x is equal to y. For x is equal to y, if x is equal to y, then you can write twice x is equal to twice y, right? So in that case these two gonna be equal. So we can say that for x is equal to y, we can write del u by del x is equal to del v by del y. So that's supposed to be v. Okay, del v by del y, right? So now these two are already equal. It is clear from the above analysis. So now here you see these two, twice x and twice y. For x is equal to y, twice x equal to twice y. So that's why twice x is this and twice y is this. That's why we have got this relation, right? So hope you have understood. Now you see these two both equal to 0. So that's why we can write del u by del y is equal to minus del v by del x, right? Therefore this function is analytic at all the points x is equal to y. So hope you have understood. I have taken this question from exercise of HK Das Mathematical Physics books. So we're gonna solve more problems in the next video. Okay, in the next video we're going to solve more problems, and we're going to discuss about polar form of these conditions as well. Okay, so see you in the next video. Thank you for watching. Stay connected, hit the bell icon and hit the thumbs up button, also subscribe button as well. So see you in the next video. Bye bye.